Hi everyone, and thank you for joining. I will be presenting evaluating the effectiveness of heuristic worst-case noise analysis in FHE, and this is joint work with Kim Laine and Rachel Player. Kim Laine is at Microsoft, Rachel Player is at Royal Holloway, and I am affiliated with both NTNU and Royal Holloway. I'd also like to say that a lot of this work was done while I was at Intel AI in San Diego, and I would also like to thank Rachel Player for some of these slides. So let's start with the motivation. I'm sure most of you know what FHE is, but allow me just to quickly do a recap. Fully homomorphic encryption or homomorphic encryption is a type of encryption that allows you to compute on encrypted data. And this is particularly useful if you would like to outsource a computation for any reason. So say you are the purple person on the left and you have some data X and you want to evaluate this function F on your data X. But you don't want to send your data out in the clear because it might be sensitive data. Now, what you can do with homomorphic encryption is that you can encrypt your data X and then send that along to the cloud with the function that you wish to be computed on F. So what you send is your encrypted data and a request for computing a function F on your encrypted data. The cloud receives this, is able to apply F to the encrypted X because of the homomorphic encryption capabilities and properties. And so it simply evaluates the function F on your ciphertext. It then returns the result of this, which is still in encrypted form. And then you can recover it, and then you can decrypt your ciphertext, which is the evaluation of F on X. And during all this time, your data has never been exposed in the clear to the cloud. And this gives rise to many, many applications that I won't talk about now. I'm sure all of you are familiar with this. What I will talk about instead is one of the main challenges in FHE, which is the noise. Now, typically at a high level, a little hand-wavy point of view, an FHE ciphertext is computed by picking a lattice point and adding some noise. And decryption is performed by finding the closest lattice point with some secret information. And so if you look at the picture here, we have this red ciphertext that's been encrypted by picking this lattice point and adding some noise. And similarly, the blue ciphertext has been encrypted by picking this lattice point and adding some noise. Now, as I've said to you, the main point of homomorphic encryption is that you can do operations in encrypted form. So let's add the red and the blue ciphertext, which gives us the green ciphertext. But now if we want to decrypt the green ciphertext, remember that we want to decrypt by finding the closest lattice point, which is easy in 2 dimensions, but it's hard when the dimensions get bigger, but you have some secret information. But here in 2 dimensions, for the red one, you look, this is the closest lattice point, that's the decrypted message. For the blue one, you look, here's the closest lattice point, that's the decryption. But for the green one, you can see how it's already not clear which of these 2 points is the closest lattice point. And this illustrates the fact that the noise in an FHE ciphertext compounds. And this also illustrates the fact that this noise can compound so much as to lead to decryption failure. Now, currently, we don't know of a way to do FHE encryption without adding noise. So regardless of the scheme, this is an issue or a problem that all of the schemes face, and all of the schemes implement some mechanism for dealing with the noise. And again, if this noise is too large, decryption will fail. Now, there are 2 main ways of dealing with this noise growth. One of them is bootstrapping, which will not be covered in this talk. The other one is modular switching, which will be covered in this talk. But the idea behind these is that they're both very expensive operations. And so what that means is that you don't want to do them too often. So you essentially want to do them right before the noise becomes so big that it causes a decryption failure. Because you might think, well, we have this noise problem, why don't I just do a bootstrapping operation or a modular switch after every single operation? And that would solve the noise problem, but it would introduce a really large computation overhead. And so because of this, a good understanding and a good modeling of the noise growth in a given scheme is really very important to be able to select appropriate parameters as small as possible, yet that don't give us decryption failure. And this is especially important because requiring large parameters remains one of the major challenges in practical HE, meaning in HE implementations. And so this is the issue that we focus on this paper. So we have three main contributions. The first one is to evaluate the effectiveness of heuristic worst case noise analysis in the schemes FV and BGV. And we use the Ilyashenko method and we give new heuristic bounds for BGV. And we show that these Ilyashenko bounds are tighter than previous bounds that were in the literature. And then what we do is that we compare this heuristic estimate of the noise growth to the practical noise growth in the SEAL and HElib libraries, meaning that we run experiments and we note the observed noise growth and we compare that to what we have theoretically predicted. And what we find is that although we do have an improvement over the previous heuristic bounds, there's a significant gap between what is observed and what was predicted theoretically. And we call this the heuristic to practical gap. And we also make the conjecture that the current approach, meaning the heuristic worst case, cannot tighten the bounds any further than we did in this paper. And what we do is that we propose closing this gap through other methods as an open problem. And then finally, as a second contribution, we also update the Costache smart comparison of BGV and FV. The reason for this is that it's been recently shown that the Costache smart parameters that were proposed had as little as 50 bits of security. And we redo this comparison for parameters that achieve 128 bits of securities. And what we conclude is that FV has a slight advantage over BGV, even for large plaintext moduli, which is in slight contradiction with the findings of Costache smart. But we also conclude that the two schemes are very similar, which is again in slight contradiction with the previous Costache smart findings. And so, as I've mentioned, we use the BGV and the FV schemes. I'm not going to go into too much details about how these work. The main difference between the two is the fact that BGV has the message in the lower bits of the ciphertext and FV has the message in the upper bits of the ciphertext, meaning that in FV you have this divide and round operation at decryption that you do not have in BGV. Okay, so let's move on to the heuristic worst case noise analysis in these two schemes. So we look at the canonical embedding norm. The canonical embedding of a polynomial is simply the evaluations of that polynomial at all the primitive roots of unity, and then we take the infinity norm of the canonical embedding of the polynomial, which is called the canonical embedding norm. And now the previous method for a polynomial was to bound a polynomial as 6 times square root of n times square root of the variance, where n is the dimension of your ring, meaning the dimension of your LW instance. And we use this 6 came from the fact that the inverse error function of 6 is approximately 2 to the minus 55. Now we don't change that, but what we do change is that in the previous method, what was done was that we looked at the variance after the canonical embedding. So we look at the canonical embedding of a random variable, then we multiply the two, and that's how we got our bound previously. But what we do now in this work is that we first multiply the random variables and then we apply the canonical embedding, meaning that we always use this term of 6 here even for a polynomial A that is the product of several random variables. And this allows us to get the bounds to be tighter. And then we use these facts about variances. And so that's how we get the heuristic bounds. How about how we get the experimental bounds? We choose to have a specific homomorphic evaluation for both schemes. And we run this over many trials. And in the IVE trial, what we have is that we generate fresh ciphertext encrypting I+1 and I. And then we add them together, which gives us CT3. We then multiply them together, which gives us CT4. And finally, we do a modulus switching, which gives us CT5. And then for each operation, we record the observed noise budget growth. And then we output the mean of the observed noise budget. And then in parallel, as I said, we compute an estimate of the noise growth using this worst case heuristic analysis updated with the Ilyashenko method. So here's what we find. So in this table, you have each of the 4 operations that we look at. So encryption, addition, multiplication, and modular switching. And then you also have the column P for predicted, I for Ilyashenko, and then X bar is the observed mean in here in HElib. And so what you can see from column P to column I is that we do get an improvement of a few bits. So we do tighten the bound somewhat. But if you look between the column I and the column X bar, you can really see that there is, as I've mentioned in the introduction, this rather large heuristic to practical gap, which, as I've mentioned before, leads us to selecting parameters that are larger than necessary, meaning that this leads us to have an unnecessary slowdown in implementations. So those were the results for BGV as implemented in HElib, and here are the results for FV as implemented in SEAL. Again, very similar observations. So we get slightly better improvement here from the previous to the Ilyashenko method compared to BGV, but the conclusions are very similar. We do get an improvement, but if you compare the columns I and the columns X bar, meaning if you compare what is predicted versus what is observed, there is still, again, a rather large heuristic to practical gap that remains. And so on this heuristic to practical gap, we've tried various methods of improving it. And this part will be the supporting evidence for our claim that it cannot be improved via the heuristic worst case method. So we've tried looking at different definitions of noise. I'm not going to list them all here, but we've tried many different definitions of noise for both FV and BGV. Notably, one of the tweaks we try to make is that, as I've mentioned before, in FV, we have this division and rounding, or rather division and floor operation, and which introduces an error, and that error is factored in the heuristic noise estimation. And so we tried reducing it, and we tried getting rid of that, and we implemented this, and we did see an improvement, but not significant enough to say it closed or even it reduced the heuristic to practical gap. Another observation that we made is that, well, loose bounds in this case are somewhat inherent, meaning that we are, first of all, we're bounding random variables and we're bounding Gaussians in the canonical embedding. And so, as I've mentioned before, we use the fact that the inverse error function of 6 is approximately 2 to the minus 55. And so we use this value of 6 in our bound here. Of course, in practice, we never actually see that value become so large because the probability is so low of it happening. And so we try tweaking that. Of course, an issue with this is that you can only tweak it so much because you still need a reasonable failure probability. But we did try to tweak that for the sake of the argument. And as you can see again here, on the left you have b equals 6, and then on the right you have perhaps more extreme b equals 1. which of course you wouldn't use in practice because that is too low. And you can see again that it does give us an improvement, but compared to what is observed, it's still not really good enough. It doesn't close the heuristic to practical gap. And then finally, we also note that the average case analysis seems tricky. So for example, the TFHE scheme uses an average case approach. And the noise coefficients are, in that case, are modeled as independent sub-Gaussians, and they trace the variance of the coefficients through the homomorphic evaluation. And they also verify this for gate bootstrapping. But the difference here is that in TFHE, every elementary operation that is needed can be achieved via bootstrapping on a linear combination of ciphertexts. So by linearity, it means that all the noises can be modeled in this way. But the issue in our case, so in BGV and FV, is that we do not have linear multiplication. And so this approach doesn't seem feasible, at least not in the way that is done in TFHE. And so again, it's a nice open problem to resolve this, and these are the reasons why we conjecture that the heuristic worst case approach is not going to close this gap. So finally, for the comparison part, the question that was posed in Costache's SMART paper was which scheme is the best, perhaps for a given application. This is something that we've added in now. And the CS16 paper looked at the schemes Entru, Yashi, BGV, and FV, and then compared them against one another, achieving 80 bits of security. Now, first of all, the schemes Yashi and Entru have been shown since the CS16 paper to be vulnerable to attacks on what are called overstretched parameter sets, which were the relevant parameter sets in that paper. And also, first of all, according to the HE standards, we now aim for 128 bits of security, not 80. But also, since because of attacks that have come out since the publication of CS16, some of the parameters that were claimed or at the time were thought to have 80 bits of security have now been shown to have as little as 50 bits of security. And so we've updated that, and we've used the same homomorphic evaluation as in the CS16 paper. So we had the dimension n, the chain of moduli, and then the usual standard deviation. And what we did is that we had first ciphertext, we performed zeta additions, a multiplication, a relinearization, a modulus switch down to the next prime in the chain. And then after the final mode switch, we checked if decryption succeeded. If not, we repeated with larger parameters. So we just looped through parameters starting from the smallest set until we found a set of parameters, until we found the smallest set of parameters that allowed for correct decryption given that circuit. So this is a repeat of what I just said. And what we did is that we compared the two schemes in terms of the ciphertext size in kilobytes, which we argue if you are going to compare the schemes for any parameter, this is the one that makes sense, because ciphertexts are what you compute on, ciphertexts are what you transmit. So a big ciphertext is going to, a large ciphertext is going to impact all of the efficiency of your scheme. And so here are the results for different plaintext moduli. And you can see that there are, so in orange, you can see the parameters where FV outperforms BGV. But then you can see that almost immediately after that happens, they kind of become equal again. And so overall, they are very, very similar, although we do see a slightly better performance from FV compared to BGV. But it's worth noting that this is beyond the reported crossover point in CS16, where we'd found that for large plaintext moduli over around 10 bits, BGV really outperformed FV. So this does slightly change those conclusions. And then finally, how good is the heuristic worst case noise analysis? Just for the conclusion, as I've mentioned, the Ilyashenko bounds are tighter than the previous methods, so there is an improvement that we get. However, the large heuristic to practical gap persists and remains, and we do conjecture that this gap is not gonna be improved via a worst case heuristic analysis. And so perhaps a future direction is to look at implementation specific analysis. So thank you for your attention. Here's my email. There's the e-print of the paper, and then there's also the code that we used for it. Thank you.